Hello to everyone. My name is Nati Shalom. With me is Tomer Gebel from Sears.com. Today we'll walk you through an interesting case study of a social e-commerce running on top of Gigaspaces. Tomer, hi.
Hi Nati, great to be here.
So we'll start by a quick introduction to Gigaspaces for those who are not familiar with Gigaspaces, and then Tomer will walk us through some of his experience on building the social graph on top of Gigaspaces, what been the consideration, what was the challenges, how they actually integrated with Facebook, and so forth. So we'll start with a quick introduction to Gigaspaces. So for those who are not familiar with it, we've been around for 10 years dealing with scalability problems. Most people knows us by the fact that we deal with data scalability at the beginning, and we expanded our platform later on to deal with the end-to-end scalability. We have hundreds of customers today from financial services who's been our early adopters, and in the past 2 to 3 years we've been expanding our market to the e-commerce and to the online gaming and telco world. The product itself comes in 2 flavors. One of them is called the Elastic Cache, which deal with data scalability, and the Elastic Platform, which deals with the end-to-end scalability, meaning the ability to scale not just the data part of the application, but the end-to-end part from the load balancer down to the database. With that, I'll finish the introduction part to Gigaspaces, and I'll hand over to Tomer. Tomer?
Thanks, Nati. So my name is Tomer Gebel, and I work for Delver, which is basically the Israeli R&D center for Sears. And what I'm going to talk about is a case study about our use of Gigaspaces to build a social commerce platform. So I'm going to start by introducing the business case for social commerce. Then I'm going to go over some of the technical challenges that we've encountered and how we solved them. Specifically the ones that we solved using Gigaspaces. I'm gonna introduce some key benefits to the Gigaspaces platform and the sort of difference that it made for us in R&D, and then we're gonna finish up, I believe, with a bit of Q&A with Nati. So moving on. The case study. What is social commerce? In essence, the last few years I've seen amazing growth in social networks, starting with the age-old MySpace and moving on to Facebook. The sheer volume of traffic going through these websites is astounding. I mean, some estimates today place Facebook above Google. That may be controversial, but the very notion of a social network starting to sort of bite on the heels of a large search engine is quite astonishing. Regardless, we're talking about millions of daily unique visitors, millions of users, a huge volume of traffic. So the real question is, where is the money? How do you monetize this? So first of all, I want to go over some of the differences between traditional e-commerce and social commerce and the sort of problems that social commerce aims to solve. So first we have the discovery and recommendation features. Traditional e-commerce websites build on global statistical models that are really hard to get right for any specific user. The global nature of the data makes tapping the long tail extremely hard, because typically aggregate data is based on popularity and statistical probability, which obviously does not map well to long tail products. Also, there's overly broad advertisements. Basically, users have grown weary of advertisements on websites simply because typically the advertisements do not map well to the specific visitor's interests. Furthermore, the trust model is inherently broken, because with traditional e-commerce, you go on, for instance, Amazon.com or Sears.com, you view a product, you can get hundreds, even thousands of opinions on that product, but those opinions are not necessarily right for you. Each person has different desires, different appeals, and it's very hard to gauge the sort of benefit a specific product will have for a specific visitor from a global model. Perhaps the worst thing about traditional e-commerce is that it basically isn't fun. Sure, there's some satisfaction from going on a shopping binge online, but typically the nature of shopping is social. You go to the mall with your friends. You go on a shopping spree for Christmas to buy products for your family. It's always a social experience. There's always the social context. So social commerce basically aims to resolve some of these problems by, first of all, providing personalized and accurate product discovery. The very nature of social circles and social groups is based on shared interests and common views and common perspectives of the world. So it's much easier to give personalized recommendations based on a social context. Also, because the volume of data is significantly lower, basically what this means is that the long tail is very easy to tap. If you derive a person's interests from his or her social circle, you're much more likely to find esoteric interests that can still be monetized than you are with a global statistical model. Personal familiarity with the people that you talk to means enhanced trust. That means that even a single opinion coming from a friend, a relative, an acquaintance, basically someone you know and whom you've met sort of face to face, or even over the internet, but you have a more intimate familiarity with, that person's opinion is worth more than hundreds, even thousands of opinions aggregated from the entire internet. So that takes care of the trust model. And perhaps most importantly, the whole concept is to bring the social back into the mix. Social commerce, the whole point behind it is to enhance user interaction, to enhance the sort of to give a bit of the face-to-face social value that people used to derive from shopping on the internet. So that's essentially the sort of problems social commerce aims to address. Obviously, the ultimate goal here is to increase monetization, increase conversion, and therefore increase profit. So why is this hard to do? First of all, let's take a look at a few numbers. Sears.com is a traditional, fully blown commercial retail site. It's fairly similar to some of the bigger players on the market, like Amazon, Walmart, etc. So taking some Comcast numbers, we have over 1 million page views daily. So that translates to over 30 million monthly page views. We have several hundreds of thousands of unique visitors per day, and over the holidays in the shopping season, traffic can easily spike 9-10 times as much for a day, even 2 days. I mean, Black Friday is notorious, for instance, for spiking traffic numbers. So we're talking about significantly higher load than most platforms need to deal with. Furthermore, dealing with social data is not an easy proposition. It's not an easy thing to do. There's 3 primary pain points in dealing with social networks. There's massive amounts of highly branching data. There's no data locality, and you can make very, very few assumptions about the data. So going into each of these in turn, we have massive amounts of branching data. Take, for instance, this really, really simple approximation of a social graph. We have 2 users, X and Y, and we want to answer the simple question, how is user X connected with user Y? So taking conservative estimates, if we have, for instance, every Facebook user in the world, we have about 500 million users, 500 million user profiles. If we take a very conservative estimate that each person is only connected to 100 other people, which I think is significantly lower than the real world numbers, if you want to answer the question, how is user X connected with user Y, we basically have to traverse the graph starting from X. So user X has about 100 friends, and each of those people has about 100 other friends. So to get to user Y, what we have is about 10,000 nodes that we need to visit on the graph, and we need about 100 reads from the underlying storage system just to answer that really, really simple user query. So there's really massive amounts of data involved. Furthermore, the data is completely impossible to partition efficiently, or rather it's not impossible, but it's very, very hard, and there's very little progress being done in serious research on this area. Any object can be connected to any other object in the graph in no particular order. For instance, there's no time locality. A user registering to the site today can easily be connected with one of the first users on the website. There's no geographical locality because the nature of the internet is global. The question of how to split the data becomes a very, very difficult question to answer. I think perhaps the most interesting research being done in this area is called SPAR, is social partitioning. It's an algorithm and a set of data structures that are currently being researched. There is some interesting progress being done there, but there's very little in the way of accepted truths and commonly accepted paradigms on how to do this. Finally, we have the question of assumptions. It's very, very hard to quantify a typical user. There's a very prominent long tail effect in play here. Some users may have 100 followers, some of them may have hundreds of thousands or even millions of followers. There's very little research data because the whole thing is so new that it's practically impossible to draw user archetypes. It's very hard to optimize for this. So you really can't pre-tune your data structures efficiently. There's no such a thing as a typical user. You can't say I'm going to choose this strategy because 90% of my users fall into a certain category. And really, you need to plan to give decent service and decent performance for any type of user. So to formalize the problem a little bit, we have a social graph with a very high branching factor that necessitates many loads for even a simple request. We do not have any data locality, and along with a high branching factor, that basically means that in order to serve a user query, we need a very high volume of completely random I/O. So that translates to traditional storage models such as databases and flat files being a very poor fit for the graph storage issue. Serious research into graph storage and social network composition only dates back a few years. That means there's very little data about best practices, accepted truths, etc. There's very few solutions in place. And most of these solutions are disk-based, which as you will soon see, is not a very good solution for graph storage in this context. So we basically translated all of this research into a set of requirements. First of all, we want completely in-memory storage. Okay, we have no data locality. That means we can't really use a caching layer efficiently because the hit ratio is going to be negligible at best. We have massive amounts of random I/O, so we can't scale it vertically. Okay, hardware costs become prohibitive. Basically, whichever way you divide the data, you're gonna run into a bottleneck in the hard drive spindle count. Okay, hard drives are both expensive and slow. If data access is sufficiently fast, I mean, if you can bring latency down from milliseconds to microseconds, you basically can ignore the problem of how to partition the data, because random I/O no longer becomes an issue. Also, we need a very, very clear scale-out strategy. We decided on the strategy of adding more memory or more nodes to handle additional data, and adding more CPUs or additional physical nodes to handle load. Additional requirements include MapReduce execution framework. The whole social context, how to query the graph, how to aggregate data from the graph, lends really, really well to the MapReduce paradigm. So we wanted an execution framework that allows us to execute fork join jobs on top of the data. Also, we wanted code execution on the data nodes. This is not a trivial prospect because a lot of systems partition the data efficiently and keep it in memory, but if we had to move the data from the data node to whichever client for processing, we're quickly going to saturate the network interface. There's a lot of data involved. If you remember the graph before, we had 100 reads just to answer the simple question of how user X is connected to user Y, and a lot of data is being moved around. So if we can execute code on the data nodes, we're basically limiting ourselves to the memory bandwidth, which is at least two orders of magnitude higher than the network throughput. And obviously, we're going to eventually cap ourselves on the ability of the CPU to handle the actual processing requirements, in which case the scale-out strategy of adding more CPUs or more nodes comes into play. Now, I'm an operations guy, so I had a few basically non-functional requirements to add to the mix. We wanted a platform where it has built-in fault tolerance and high availability. Okay, the system needs to be up. Basically, every minute that the website is not available, we're losing money because this is an e-commerce application. We wanted as close to zero configuration as possible. Because as soon as you run into your scale-out requirements, you're going to start adding nodes. Configuration becomes a huge hassle, and any human intervention required in the configuration is definitely an opening for human error. We wanted very well documented deployment, configuration, and tuning processes, and some sort of management and monitoring APIs, so that we can track what's going on inside the cluster, and so we can have an effective deployment infrastructure in place. And we wanted some sort of administrative client for diagnosis, trouble resolution, and troubleshooting in case it's necessary. So basically, all of these features map really well to the Gigaspaces feature set. Gigaspaces offers us a data grid for keeping data in memory, a compute grid that's capable of MapReduce execution on top of the data nodes. It's got built-in high availability and fault tolerance. The scale-out strategy map precisely to our requirements, and it's got a very full-featured and well-documented management API that we use for deployment, monitoring, and even ongoing tuning. There's not a lot of available alternatives, some of which are written here. For instance, Hadoop and Neo4j can definitely be used for graph storage, but are disk-based. So if we chose those, we would have run into the hardware performance bottleneck very, very quickly. Terracotta is an interesting solution, but it's overly simplistic and it has no execution framework. And one of the bigger competitors is Oracle Coherence. It is a lot more expensive than Gigaspaces for our use cases and has a significantly limited feature set. So what we ended up with is basically a hybrid platform. We use Gigaspaces for graph storage and for executing the graph traversal, querying, and analysis jobs. We use MySQL for traditional simple data storage, such as storing user data or product data. We also use it as a persistent backing store for Gigaspaces. We have a .NET-based front end and a Java-based back end. Java is a natural language for working with Gigaspaces, and our team is very comfortable with it. And what we eventually had to do was to factor our organization accordingly. We have a data access team that provides data abstractions on top of Gigaspaces and MySQL to the other teams.
Thomas, thank you very much. As usual, I always learn from those sessions, even though we've gone through them several times. I always learn new things. There are several questions that usually brought up when people discuss partitioning and data partitioning and query. What is the type of performance that you are getting, and what type of queries that you're actually executing in this platform today?
Okay, well, that's a broad question, so I'm gonna try to reduce it to a few simple answers. First of all, the query that I used as an example, which is how are two users connected, while an actual real-world use case is not really a complicated query to perform. What we have is depending on the use case on the website, depending on whether we're viewing a product page or search results, we have different types of data queries running on the system. So the required latency cap is dependent on the use case. For instance, for search results, we're going to want to show breadcrumbs between the searcher and the user who added, for instance, data on the product in question. So we're going to show you're connected to this user via another user who's your friend. So that maps to the example I gave before. Other use cases may be we need to re-rank search results from regular textual search on the product database according to a social context. So we're going to have to basically render a social graph of the user and feed it into the search engine for ranking. Other examples may be showing a news feed. Okay, user walks into the website, so to speak, and we show recent activity on the website. So there's really all sorts of different queries running, and if we want to go into numbers a little bit, typically between 1 and 10 queries on the social graph are executed per each page view. Each of these queries typically ranges in latency from a few short milliseconds to, for instance, search can take up to 200 to 300 milliseconds for an acceptable user experience. So it depends. It really depends on the use case. But with 30 million page views per month, that translates to anywhere between 100 and 300 queries on the social graph per month. So that really translates to very high performance requirements and very low latencies. We're talking up to a second for a full page view rendering, including artifacts and everything else. So we can't go to disk. Okay, that's basically the takeaway here. If you put the data on disk, since you don't have any data locality, you can't really cache any of it, you're going to run into the hard drive bottleneck. That's completely unrealistic.
Okay, thanks very much. That's, again, very useful. The other question on that regard is, you mentioned that using, you partition the data, and you mentioned SPAR as the algorithm, was one of the algorithms that is used in the industry today to study how to partition the data. And then you mentioned the use of MapReduce. How do the two combine together? Why do you need MapReduce? Why can't you just use SQL and joins and things like that?
Okay, so ideally with any type of data, what you try to do is you try to create data locality as deep as possible. You want, for instance, to say, if I want to answer any question on a single user, ideally, I'd like to be able to have all data in place for one sequential read. In practice, it's not possible, because if you want to, for instance, answer the question, which are the 10 most interesting users on Delver today, you're going to end up going through all the users and all the user data. If you can't realistically have all the users on a single node at any given time, that means you need to partition your query the same way you partition your data. If not all user data can be contained in one node, you split the data to 3, 4, 8, whichever number of partitions you need. You need to be able to run a subset of the query on each subset of the data and then combine the results. So, for instance, with the question, which are the 10 most interesting users, what you end up doing is you end up sending the query, what are the 10 most interesting users, to each of your data partitions. I mean, take 1,000,000 users, divide them into 4 partitions, you have 250,000 users per partition. So with each 250,000, you can answer the question, which are the 10 most interesting users? And then you can combine those 4 answers into one overall answer to your query. The difference between social data and other types of data, more traditional data such as the finance sector, is that you can't really generate complete data locality. You can't have all the data for a single user kept on a single node. So solutions to this problem include denormalizing the data, having redundant data on several graph leaves, for instance, in order to have all the data you need on every single partition. There's all sorts of strategies that you can put in place to solve the join problem. But once again, the main take here is that as soon as the data is split up into more than one physical node, you can computationally do a join, but it's not a practical choice because you need to move a lot of data around. So what we do is we simply divide the data more or less randomly. SPAR is a more advanced way of doing things, but it's still very, very early in the research to have any fundamental use for us, and the cost is quite high to implement it. So we divide the data randomly. We simply issue a subset of the query to each subset of the data. And we keep all the necessary small bits of data around on each node in order to answer, for instance, a query, which are the interesting users. Eventually, the bottom line is you can't really do joins on distributed data. As soon as you have a very high volume of data, you're going to run into that problem regardless of the data type. Of course, assuming that you can't have really good data locality inside your data model. Social graph does not lend well to vertical partitioning.
Very interesting. So if I summarize, then this answer and the previous answer. So one thing is use memory instead of disk to ensure the latency is consistent. Yeah. And the second one is use MapReduce to parallelize the query, and then use locality, meaning the execution framework, to actually run at least part of the query within each node to leverage, again, the locality of the data to reduce the traversal overhead and the streamlining of the entire set, just to get an answer for your questions. I think that's kind of the three main points.
The one final point is that you need to be very careful when architecting your data model, because not having the ability to do ad hoc joins efficiently means that you need to plan ahead to the types of queries you're going to be running on your data. So you need to be a lot more careful with the choices you make regarding how to model your data inside whichever storage solution you end up using.
Very good. The last question, because we're running out of time, and again, we can probably spend hours together on those interesting issues. Was you mentioned the admin API, and you mentioned, I think in one of our discussion, the continuous deployment and the need to change the data models and also to update the site in a regular basis. I hear that more on e-commerce for whatever reasons. Can you, first of all, start by describing what is the demand like? Why do you need to update the site so regularly? And second, how do document model or the admin API on the other side helps you on doing that?
Well, I'm going to divide the answer into two parts. First of all, there's the why. It's really a question of business. With internet-based businesses today, you need to be able to move quickly. Typically, the requirements change very, very, very rapidly. The user expectations change very rapidly. It's still not a very well understood market, unlike certain other sectors where it's much easier to predefine your requirements. So the need to move fast, in our case, translates to the need to be able to push a new version of the website, a new version of the data model, practically on a daily basis, and sometimes even on an hourly basis. So this brings me to the other part of the answer, the mechanics of it. How do we do this? So we're currently transitioning to Gigaspaces 8.0. Specifically, there's quite a few interesting features for us, but perhaps the biggest feature for us on the new version of the platform is the document store. Basically, there's two realistic ways to handle changes in the data model. One of them is to have some sort of side-by-side deployment solution where you have two versions of the data model running concurrently with some sort of a replication channel between them. And the other more common and possibly easier way to handle this is to have a schemaless storage model. The problem here basically is schema changes. You need to have code working on an initial version of the schema working alongside code that expects a different data schema. So with the document store, the big advantage is you can have a common data model that doesn't change very often, that includes indices and templates and all that jazz. And you can have a lot of sort of free-form metadata fields in place that can change quite rapidly, but not affect the core of your product. So with the document store, it's a lot easier to do that because we don't have to predefine our data model structure in terms of Java classes, Java objects. We can just have a core code base running against a core sort of object model, as I say, including indices and templates. And the rest of the code basically just needs to play well with either missing data in case of data being added to the model, or remove data in case of the fields being deleted, or type changes. So a schemaless object model such as document store lends really well to being able to have two versions of the code base play well with the same data. That allows us the flexibility to move from version to version very quickly.
What about the code? I mean, how do you handle changes in the code? And you mentioned that using execution.
Well, obviously, there's also several strategies in place here, but what we're currently evaluating is basically having a single processing unit handle the overall data storage model, including the tasks that belong in the core code that doesn't change very often between versions. And we're going to have code being fed into the execution grid from the client side that can change between two concurrently running versions of the application. So we have the basic code that's very robust and well tested, and we have sort of prototype code running all the time that works against the less critical fields inside the same data objects. We only have a single processing unit defining the data model, and the clients issue their own execution blocks. So each version of the client has different execution blocks, different jobs to run on the cluster, and they don't conflict that way.
Thank you very much. Again, we could continue those discussions, and I have lots of them in my head right now going on. But we'll end up right now. Thank you very much, Tomer, and thank you everyone for listening. Thank you.